Now let's once again look at our favorite equilibrium equation. A plus B produces C. I'm making all of these gaseous for right now. You'll understand why. But what we want to do is let's take a look at LeChatelier's first principle. Again, LeChatelier's first principle stated that a change in concentration, whether it be of my reactants or products, will cause the equilibrium to either shift to the right or to the left to help reestablish what the original ratio was. So for this example, what I'm going to do is I'm going to write up the equilibrium expression. This is going to be fairly straightforward. We're going to say that K, let's just make it a concentration one, so let's call it Kc. So Kc is going to be the concentration of C over the concentration of A times the concentration of B. I am purposely using concentrations. You'll see why in a moment, but I do want to talk about this in terms of moles per liter, okay? And so for our purposes, because we're going to make the world's easiest equilibrium, right? Let us just say that for our purposes, in this particular case, K equals 1, okay? Now, in order to get that, what that means is that at equilibrium, the concentration of A equaled the concentration of B, which equaled the concentration of C, and they all equaled 1, right? So you have 1 over 1 times 1. Everyone is 1. So for now, let's keep it simple, and let's pretend that we have this equilibrium. It is established, and under these circumstances, the concentration of everyone is 1. Okay, great. So K equals 1. So now, to my reaction to this A plus B produces C, I now go ahead and I add more of C. So this concentration shoots up. All right, well, if the concentration of C shoots up, well, what would happen? Let's now create a new scenario. And in this scenario, what that means is that A and B will still equal 1, right? But at this particular moment, what we're seeing is that now C is going to equal, let's increase it, let's make it 2. Now, if that's the case, that means that at this moment, then I have 2 over 1, so my new ratio becomes 2. So the real million-dollar question is, what does this 2 represent? Is this my equilibrium constant? And the answer is, no, it's not. This is my new ratio at this particular moment when the concentration of C was increased. And so when I say that my new ratio is 2, what I'm actually saying is that the reaction quotient is now 2. So now we need to make our comparison. Well, 2, Q is going to be greater than K. 2 is greater than 1. And if this is the case, which way did Pac-Man have to go? Pac-Man is going to chomp to the left. Or, let's put it all into perspective. If I put more products into the equilibrium, so it was balanced, it was happy, and now I shoved a bunch of stuff on the right, that's too much stuff. I'm now product heavy. How will my equilibrium shift to compensate? Some of the C has to disappear and go backwards, right? It's got to go back from where it came, because if it doesn't do that, then my equilibrium is now destroyed. So notice that by altering concentrations, really what we're doing is we're altering the value of Q. Now, I could have done this whether I added Q or I added, let's say instead I added more B. So let's say that the concentration of B now shoots up. Well, what's going to happen? In this scenario, let's just now make B, let's let that have a concentration of 2 molar, right? So same thing. I go to set everything up. I'm not going to have 1 over 2 or 1/2. So that means that Q is now less than K. Well, if Q is less than K, which way is Pac-Man chomping? Pac-Man is chomping to the right. Or, to put that into perspective, when my concentration of reactants shot up, in other words, now I have too much of them, now the denominator got too big. There's more reactants than what we need. So to compensate, the reaction's going to shift to the right-hand side. It's going to shift to the right to make more of my products. Now, one pro tip, because I often see this question asked and it will sometimes throw students. Let's take this scenario where I, for a moment, increase the concentration of B. Once equilibrium gets reestablished, what's going to happen to my amount of A? And so in order to help us see that, let's plug our values in. So let's pretend for a moment that I started off with 1 molar of C up here in the numerator, and I had 1 molar of A and 2 molar of B. So only B has been altered. B has gone up. We know the reaction is going to have to shift to the right. Well, what's going to happen over time? When equilibrium is reestablished, okay, what that means is that the concentration of C is going to go up by an amount, whatever it is. The amount of A is going to decrease by an amount, and the amount of B is going to decrease by an amount. Now, here's the big loser in this whole scenario. The amount of A will never again be over 1 or higher. It's always going to be less than. But students sometimes ask, well, will the concentration of B drop all the way back down to 1? And the answer is probably not. Because again, remember, while both of A and B, the denominators, are decreasing, they are going down, no one's taking that away, understand that while they're decreasing simultaneously, my numerator is increasing. This guy up here is going up. So my guess is that if the denominator goes down by a little bit and the numerator goes up by a little bit, that's going to make, when those two things are combined, a larger change or a larger shift. Okay? And this is how the idea of changes in concentration affect how an equilibrium will shift or move around in order to try to reestablish that equilibrium. Okay? Every alteration of concentration represents a change in the value of Q. We then have to make our new comparison. Did Q go up? Did Q go down? And the reaction then shifts accordingly. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.